This section covers another one of the detailed support specifications for our analysis process model. It's where we specify business policy via the contents of the lowest level detail processes. In other words, the actual step-by-step business rules or instructions. I use the word policy for the essential processing and analysis as opposed to the word procedure for the processing and design, which may also contain additional instructions to accommodate the design. In this section, we get to use some basic specification methods from our schooling system. Our process models, for example, the data flow diagram, are certainly a form of process specification, but they're at least one level above detail. They're not intended to show individual instructions. We use a model to break down complexity so we can get down to the specification level we address in this section. In the absence of a model, I've seen way too many huge volumes of text used as the documentation for an organization. These are usually left on a shelf and never looked at. Graphical models help reduce huge volumes because a picture can be worth 1,000 words. But we'll probably need to back up models with words at some point. For example, I can't imagine having a textual document replacing any map of a country. But even on the lowest level map, I still want to see street names and monument names, etc. In this section, we're going to cover drilling down to detail using the process model, specifying detail processing, methods of specification, capturing business processing and policy, overcoming complex processing, using decision tables to obtain accurate policy, sample decision table, capturing precise policy using structured English, and an example of a formal and informal process specification. Let me set the stage for this section by repeating the concept of leveling and partitioning process models from a previous section. We talked about using leveling and breaking down processes by drilling down to the detail using the process model. In analysis, individual process specifications are used to declare the business policy, as opposed to a solution procedure, governing the transformation of input data flow or flows to output data flows for each lowest level process, functional primitive, on a process model. Remember, we break down and level processes on a process model until we reach functional primitive processes. This is the level where we stop using a graphical model and specify detailed processing. If you recall, functional primitive processes can occur at or below the event reaction context level. Specifying the detailed processing, the business policy, for each detailed process should be relatively easy now that we've used a process model, such as the data flow diagram, to break down any large process into small functional primitive processes. So once we have used a process model to partition and document the flow of data in an event reaction throughout the organization, partitioned and documented the stored data needs, defined the model's data in the data dictionary, and reached a level of decomposition of the processes where the transformations of data and/or controls are at the functional primitive level, we can now specify the processing detail of input to output data transformations. Only now in business process analysis, we've used the graphical process model to enable us to have small, manageable process specifications to document, not one big specification. So for any one process specification, we only need to focus on just how the incoming data flows to a functional primitive process create the outgoing data flows from that process. Obviously, we can only use the flows shown in and out of the specific process we're addressing on the process model. For example, in the partial diagram on this slide, we need to only concentrate on how the valid customer order, along with the stored data elements of product price and tax amount, are used to create a customer invoice. If we find the need to use other flows as we specify the detailed processing, we must go back and change the process model and maybe the data dictionary. So at this point, we can utilize the basic methods of documentation that our schooling system gave us. The step-by-step rules for transforming inputs to outputs are specified in small, typically 1 page or less, process specifications. We can select from several forms of representation, such as graphs, charts, decision tables, decision trees. Notice that those 4 forms of specifications still employ graphics. Algorithms, if the process is a calculation. Just ordinary narrative written textual instructions written the way you would speak. And if the written text could be read ambiguously, then we can use a rigorous form of English called structured English. We'll talk about a couple of these that I think will be helpful on the following slides. Note that for any one process specification, we may combine any of these forms of specification as appropriate. I've shown an example of such a combination on the lower right of this slide. It uses text with bullet points and a decision table to specify a process. I should also state here that whereas textual specifications are quite common, we should also use audio and video as a means of specification, especially as I'm using that media to teach this subject. The overriding theme of analysis versus design issues I keep talking about in this tutorial obviously applies to detail processing also. The intention here is to specify only the essential business policy, not human procedure or computer logic. In other words, no design characteristics in the processing. Remember, for the analysis specification to be used as input to a new design, it should not limit the designer with unnecessary restrictions. In this tutorial, I mentioned design issues that I said should not be on the analysis model. I'm going to repeat those design issues, but this time I want you to apply them to individual process policy, the instructions, within our process specification. So the individual analysis process specifications don't show processing associated with human issues such as human errors or corrections of them, backup restore of human files, internal human audit traces, external audit traces are valid, management sign-offs and approvals, human timing issues, business timing is valid, physical media of data, for example paper, file cabinets, human data access issues, for example folders in a cabinet in alphabetical ascending order, sort, merge, extracts of paper or folders. Analysis files are similar to the human brain, access anything in any order. The analysis process specifications also don't show processing associated with computer or automation issues such as computer errors or corrections of them, backup restore of computer files, internal computer audit traces, computer system timing issues, computer macros subroutine calls, physical media of data, for example communication devices or databases, computer data access issues, for example relational access methods, sorts, merge, extracts of computer files. Now that's just the design issues I can fit on this slide. At this point I hope you can fill in more design issues for your particular organization. A process specification's business policy should not presuppose any particular implementation environment, human or computer, or any particular implementation hardware or devices. I've shown a diagram on the lower part of this slide to indicate that having removed all of the design issues, our process specification should be capable of being transformed in the new design into either human procedures or computer logic. Be careful when extracting business policy from existing documentation, because at this level we may find the existing business policy is archaic. So it's at this level of detail that the policy owners and business users have an opportunity to examine the organization's policy for correctness and applicability to today's business environment. I tend to use the generic words what and how to separate analysis from design. It's at this point where I can say those general words break down. One could say, looking at a process specification, that it describes how we transform input into outputs, and that would be true. At this point in the tutorial, I hope you can see the finer details of analysis versus design. Now, the specification of a functional primitive process is usually so small, for example 1 page or less, that the classical documentation tool of narrative textual instructions can be used effectively. However, better tools can be used, especially where the logic is complex or could be read ambiguously. There's a valuable graphical detail specification tool I've been using and teaching for decades. It's called a decision table. I used to like to use them when I was a computer programmer. They helped identify any missed logic in my computer code. They can also help overcome complex decision logic when the tool of procedural written text breaks down. Suppose we had a process on our process model shown in the example on the upper right of this slide that calculated a customer discount. It uses as input a customer order consisting of at least 3 data elements: the customer payment, the customer type, and order amount, and produces a customer discount amount. In talking with a current business user or member of staff in the organization, we may get the interview notes for the process calculate customer discounts shown on the left. If customer payment is by cash, and if customer type is regular, give 15% discount. Else check to see if the order amount is for more than $1,000. If so, give 15% discount, otherwise give 10% discount. Else give 7% discount. Always give 5% discount on orders over $1,000 on our company credit card. These interview notes try to account for each condition with a corresponding action, but it still seems confusing. By the way, I used to apologize in my live analysis seminars for this particular example being deliberately confusing, but so many of my students would say, no, don't change this example. This is what I usually work with, not to mention some of the convoluted existing computer code I see. So I stopped apologizing for it. Now, for policy with this type of complex decision-making logic, it's best to draft out a decision table, or tree, to ensure all the correct policy is captured. Let's do that on the following couple of slides. Decision tables and trees have been around for a long time, and there are whole books on how to create and use them, but I've just used the simple rules on the following 2 slides to teach and use them in my professional career. There are 5 relatively simple steps in creating a decision table. Step 1. Identify the conditions stated in the process, values of each of those conditions, and actions that can result from those conditions. In the interview notes from the previous slide, there are 3 conditions stated. Note that conditions are usually preceded with the word if or an implied if when someone tells us the procedure. In our example, we have 3 conditions: customer payment, customer type, and order amount. Each condition has 2 values. The values of those conditions appear to be cash or credit card for customer payment, regular or non-regular for customer type, and over $1,000 or not over $1,000 for order amount. These value ranges obviously need to be confirmed with the business user. For example, we would ask if there's a payment by check option also. Basically, we have one action to give different discount amounts based on each set of conditions. We may have multiple actions in some other example, but not on this one. Step 2. Calculate the total number of combinations of conditions that can occur in the process. This will determine the number of columns in the decision table. This is a simple calculation where the total number of possible combinations of conditions equals the number of values in condition 1 multiplied by the number of values in condition 2 multiplied by the number of values in condition 3, and so on, if we have more conditions. We don't in our example. Now we only have 3 conditions, and each one of these has only 2 values. So we have 2 times 2 times 2. 2 values for customer payment multiplied by 2 values for customer type multiplied by 2 values for order amount. So we have 8 columns in our decision table. If we had had one more value for customer payment, we would have had 3 times 2 times 2. So our table would have had 12 columns. As we can see, these tables can get quite large depending on the number of values of each condition. But remember, we've used a data flow diagram to break down complexity, so our processing should be for small primitive processes. Step 3. Draw the decision table with 1 row for each condition and 1 row for each action. We have 3 condition rows and 1 action row. We could have drawn many action rows with a discount value for each row, but as we have a single action to give a specific discount amount, we can condense this into 1 action row with action values in the action row boxes. We also draw 1 column for each possible combination of conditions. We have 8 combination of condition columns. So we will have a decision table that looks like the one here on this slide. Just at this point alone, you can see we end up with 8 triple compound conditions in the processing, each one of them unique. I doubt the interview notes on the previous slide can cover all those conditions in such a short statement. Let's complete the example on the next slide. I've filled out the table on this slide from step 3. Step 4. Use the following simple calculation to fill out the condition columns with all possible combinations of values. Start with the first condition line. It doesn't matter whether we start at the top or bottom condition. Decision tables are non-procedural, although we can recommend a sequence in which to check the results. The number of repetitions for each value for the first condition line is equal to the total number of combinations of conditions, that's the number of columns, we have 8 columns, divided by the total number of values that this first condition can have. In our example, we have 8 columns with 2 possible values for the top condition, customer payment. So our calculation is 8 divided by 2, which equals 4. So we start to fill out the decision table for this condition line with 4 repetitions of one value, and then enter 4 repetitions for the next value, and so on until the end of the condition line. Again, it doesn't matter which value we start with. In our example, we can repeat 4 values for cash and 4 values for credit card in the top line. For all other conditions, we do the same simple division, only using the number of repetitions from the previous line as the number to divide into. So we have 4 repetitions from the previous line divided by 2 values for this next condition, customer type. 4 divided by 2 is 2. So we fill out this condition line with 2 repetitions for each value. Again, it doesn't matter which value we start with. And we keep doing that same simple division until we have completed all condition lines of the table. In our example, for the last line, we have 2 repetitions from the previous line divided by 2 values for this last line. 2 divided by 2 is 1. As you can see, I have a keen grasp of mathematics. By the way, the last line should always have a repetition number of 1 because we multiplied up to get the number of columns, and now we're dividing back down to get this repetition number. Step 5. Identify which action goes with each set of values, working from the user statements. In other words, evaluate the action, or actions, to take based on the set of values in each column in the table. Now I'll let you try to fill in the action boxes, but I have to admit here, I set this example up where the user statement, a couple of slides back, never explicitly states 3 conditions at once, but we could assume some things based on the statements. So the answers vary greatly when I do this small exercise in a live seminar, making the point to be careful when using written text for complex decision logic. Finally, we verify the result and resolve any questions with the business user policy owner. In this example, there are lots of actions that we don't want to make any assumptions about in this table. As analysts, we are not business policy creators. However, if this was a real example, we can guarantee that all possible combinations have been accounted for in the table, and the correct policy can be obtained from the appropriate user policy maker. I'll mention here that I have had students tell me that when they have gotten to this level of specification in their organization, they have sometimes found bugs in production manuals and computer code. If our business user is not already familiar with decision tables, we may find them making some interesting comment, such as, "Can that happen? And I never thought of that situation." Also, talking with business users, we may find some combinations of conditions are not valid in the real world, so we would just indicate that with a not applicable note in the table. A decision tree is a very similar specification tool and uses the same steps I've just talked about, but creates an expanding tree based on the values leading to the actions. I've shown the equivalent decision tree for our example at the bottom of this slide. A complex policy that does not lend itself for easy specification using written text or even decision tables, etc., we can use structured English as a rigorous specification tool. In my early days as a computer programmer, I was taught what was known as structured programming. It was an easy way of structuring computer code to make it easy to follow the logic. It uses 3 basic structural building blocks to do this. Even though we're not going to do any coding, and certainly should not in analysis, we can still use the same ideas to structure our business policy into an easy-to-follow, readable form, especially where we have complex policy. Structured English is a very exacting form of English, without loose or ambiguous words. It too uses 3 building blocks to specify any policy. It also recommends we write 1 instruction per line, along with graphical indentation, spaces, to bring attention to subordinate instructions. The 3 building blocks can be described as sequence, a way to order instructions, selection, a way to choose one or another option, and iteration, a way to repeat some instructions, usually until or while a condition is applicable. In other words, we only use sequential instructions that are read one after another, This is using single instructions, for example, calculate, move, add, multiply, etc., in a linear order. This one is somewhat natural as text is read in a linear order. We use some way of selecting between instructions, such as an if-else decision, and we use some way to show iteration instructions, such as a for each loop or a do something repeatedly until or while loop. The example on the right shows all these building blocks used together in one set of cryptic policy. Notice the indentation, the use of spaces in front of instructions, to indicate subordination of instructions. I've shown dashed vertical lines to show the subordination levels. The summarized policy in the example shows that we calculate something, then check a condition, and if it's true, we do some true condition instructions. The rest of the processing is performed in the else part of the condition, that is, if the condition is false. The false part does some false condition instructions and then checks another condition. If it's true, it does some true condition instructions. If it's not true, it does some false condition instructions. Now notice where the for each loop statement is positioned. It's in line with the if-else before it, which means regardless of that last previous condition, true or false, we're going to perform the repeated instructions. So the three building blocks of structured English can be nested within each other. This structure applied to the business policy makes it so we cannot read it ambiguously. This is the benefit of using structured English as a form of process specification. As structured English may be new to most people, I'll include an example in this last slide of this section. There's not much to teach about structured English, it's just non-ambiguous, pruned-down English. Maybe that's the whole point of using it when needed. So all I want to do with this slide is show two examples of the process specification for the process assign new project, shown in the process model data flow diagram on the top right of this slide. I've taken two examples of the same process specification from one of my earlier books titled Developing Quality Systems. The top example is formal structured English. As we can see, it follows the rules of one instruction per line and the use of indentation. The bottom example is just non-ambiguous English, written pretty much as one would speak. Both are correct and can be easily turned into a human procedure manual or computer program code. I don't want to go through this policy in detail, but just show them so you can see the different styles. You can pause and read through the different examples if you like. I tend to find people who are technically oriented like the top formal example, but those who are business-oriented like the lower informal example. I remember in one seminar where the attendees were all business users, someone said, "I went on a programming seminar once and I've not been the same since, so don't show me that formal structured English stuff." As long as the policy is non-ambiguous and complete, use whichever you prefer unless there's a standard in your organization. For those who like the formal example, let me mention here there are a couple of additional features I like to use when I create a formal process specification. As we can see in the top example, all data elements are in uppercase and hence use the exact names that are in the data dictionary. They are, of course, also in the data flows in and out of the process model process. All words that have their first letter in uppercase get transformed into human instructions or into a particular computer language's instructions, depending on their implementation. As I said before, we don't have to write all our process specifications in structured English. It's just helpful when the business policy could be read ambiguously in normal text. Remember, our goal as a process analyst is to create a business process specification that can be understood by anyone required to verify it, build a system from it, and maintain it.